Good afternoon. I would say good morning, everyone. Thank you so much for inviting me here to this conference. My name is Tony Young, and thanks for the wonderful brief introduction. Today, my presentation here is about a research work that I have worked with Professor Jack Maley about 20 years ago, and it's picking it up, and then it's a bit of a summary where the theory has about and where the implementation and where we're going from here. So I prepared the topic as performance-based earthquake engineering from concept to implementation to the future. Okay, so I get started here. The first slide here shows performance-based engineering. We heard about that quite a lot. Everybody have different way of explaining what's performance-based engineering. So about 20 years ago, Professor Maley presented this slide, and he go around and look into the literature, and he found this quotation. If a builder build a house for someone and does not construct it properly, and the house which he built fall in and kill its owner, then the builder shall be put to death. That's how clear performance objective is, 1978 BC. So build something, don't collapse. And very clear objective where we needed to match. And we're glad we're not doing that anymore. That's why we have lawyers today. So over these hundreds of years, we have evolved significantly into performance-based earthquake engineering. And different than before is that now there's a lot of uncertainty into earthquake. But in general, we understand there are small earthquake, which comes every 50 years, and then it causes some shaking. And we have some expectation that when a frequent earthquake happened, we wanted the building to withstand the structure shaking, but not too much damage. We expected the wall could have some hairline cracks, but the electricity and water still running. So we can go there and repair after the hours. We can go and repair that the building can be good. And if a big earthquake comes every 500 years, 1,000 years it comes, we want to do everything we can to make sure the building do not collapse. And that's why we started talking to our colleagues in here and around the world. This is what we expected what performance-based earthquake engineering should be. Okay? Even though this become very natural to many of us sitting in this room today, to the building owners, it's a big question to them. You tell them what's immediate occupancy, collapse prevention. What they really care, it's not these numbers. What they really care is that if a magnitude 7 earthquake hits my building, how much money am I paying? Okay? How much downtime I expected this facility will be shut down? Okay? And if needed, what's the casualty rate I was expected to see so they can make some decision making? So the question is that how do we go from something we know very well, the behavior of the structural system, into quantity that we can start making decision making? Okay? How much downtime we have. Over the last 20 plus years, Pacific Earthquake Engineering Research Center actually presented this very famous peer triple integral equation, and I represent it here. And when people look at that, they say, wow, this is crazy, right? I mean, engineers looking at this, their eyes started spinning in their head. To be really honest, many professors, when they look at these equations, their eyes start spinning in their head too, right? When's the last time you're dealing with conditional probability, product conditional probability 3 times and integrate it? And how do we really make use of something like this into engineering practice? Well, this is very, very mathematically difficult, and I had a hard time myself learning that and started trying to explain that in a simple term. But it's a very good framework, started putting people together from all disciplines in earthquake engineering. Now, the left-hand side, we're representing what owners are looking for, the seismic risk. How much money am I expected to pay if a magnitude 7 earthquake hits this building? On the right-hand side, it breaks up this big problem into 4 parts. The first part is the probability seismic hazard analysis. I'm sure there's a keynote speech yesterday where I talk about if I'm here in Taipei or I'm in Tokyo, what kind of seismic ground motion I should be looking for. So that's the first portion of that. Once you have the ground motion, the second phase is we're going into, now I have this shaking happen to this side, what will be the structural responses I should be looking for? So you go from ground motion to structural responses. Once you know what's the structural responses, the next thing to go in is the structural damage. If my building is going to move to 2% interstory drift ratio, 5% interstory drift ratio, what's the expected damage to that? And lastly, if you know what's the structural damage, then you can go and repair it. So you can go from structural damage, finally going to monies, right? How much money I expected to pay if an earthquake happened to my facility. So this becomes the famous peer three-point integral equation where we start working together. Well, for many engineers, of course, they hated this one, but the concept is very simple. And how do we really implement it? It's really not very difficult. Literally 20 years ago, Professor Whitaker, Professor Maley, we were working around a building. Let's pick a building just to show our colleagues in California how to do that easy. It's not difficult. So step number one, pick a building, and you have structure drawings, so it's very easy to do. And then that's a building at UC Berkeley. And all we have to do is start looking what are the different kind of earthquake were likely to happen to my particular site and during the design phase or whatever I'm evaluating for. So for those of you who are not from the Bay Area, Berkeley is in a highly seismic zone, lots of earthquake faults around it, and this is where the Silicon Valley. Okay? So once you know what kind of seismic hazard in that particular location, it's not difficult. We have many good seismologists tell us what kind of earthquake we should be using for assessment and design, so we can pick ground motion. Once you have the ground motions, the next phase is build up a computer model, okay, which we train our graduate student, undergraduate student in coming out with nonlinear, sophisticated computer model that we can study the response of the structural system. Okay? So we can quantify how much is the drift, how much is the acceleration, how much is the forces in each of the beam and column or in the wall. From there, the structural responses we call the EDP, engineering demand parameters. So with that, we can go and quantify what will be the structural damage. Okay? So ACCCS initiated, I think, in the early 2000, around mid-2005, where many of these really leading-edge structural engineering professors are working together and try to help the industry to answering the question, how much money I expected to pay if a magnitude 7 earthquake hits my building. So they publish a series of database. Okay? So in here, this is still from ACCCS project. Over here, it says that, if I have a flexural controlled concrete shear wall, and there are many modes of failure, and on average, okay, the median, on average, if the interstory drift ratio was 1.5%, we expected the concrete core wall will have some cracks, hairline like the one we're showing on the picture here. As the drift increases, okay, we'll see some of the cover concrete started to spoil, and on the very extreme cases, more concrete will spoil, and maybe the steel rebar will buckle. Okay. So this information, once you know the structural damage from here, structural engineers have very good ways of retrofit them. By looking at this kind of structural damage, many structural engineering professors will say, oh, the wall is kind of plumb and straight, and I see many hairline cracks, so probably my steel rebar are still straight, okay? Then probably the wall is as good as new, so they provide a recommendation, maybe we epoxy filled it and we repaint it, the wall is as good as new. Okay? And if I see a really bad structural damage where the cover concrete already spoiled, where the rebar already buckled, maybe I have to jack it up first, cut the steel bars and resplice it and report the concrete. So the actions are available. If you know exactly how you're going to repair for it, then you can give these kind of repair actions to construction companies, and then they can tell you how much does it take to repair for the wall like this. Well, then you will say, okay, I'm going to go charge you around $4 US dollars per square foot, up to $800 square foot. If you have a lot more for me to repair, to epoxy fill it and paint it, maybe the price will reduces to $2 per square foot. So different kind of repair damage will have an associated repair cost to it. So sometimes, many of the professors here and researchers here are in the laboratory, and if you test the wall twice, chances are they are similar but never identical, right? Because there's material inhomogeneous and many things, quality of construction. So we started looking into, okay, there will be some uncertainties. When the drift was 1.5%, it may be here, it may be here. Okay? So then we started presenting this kind of results into what we call the fragility curve. Fragility curve, the y-axis here representing probability, horizontal axis here representing whatever engineering demand. So in this particular case, this will be the fragility curve for the pictures for the table I showed previously. How do we use it? Okay, basically, if I have an interstory drift ratio of 3.5%, the fragility curve is telling me that I have about 50% probability I will be in this damage state. I have about 35% probability I will be in this damage state. I have about 15% probability I will be in that damage state. And chances are at 3.5% interstory drift ratio had 0, no crack, probably are very, very low. So it's not too difficult to get a ground motion at this stage. The Pearce Center has published many ground motions. Anchorage Center have the ground motions. And many research centers around the world publishing the ground motion appropriate for the site. Getting a computer model is no longer difficult. We started training our engineers to put the computer model and quantifying the structural responses. From there, if I know what's my drift, let's say 3.5% interstory drift ratio, and I have different probability the wall will be in any one of these damage state, so I will throw a random dice. And if the dice stop here, I know my wall is in damage state 4, okay? So damage state 1, no damage. Damage state 2, lightly damage, severe damage, and almost collapse. So in that situation, you know that particular wall is in that damage state. You know what repair action you need to do for that wall. You're going to take out the spall concrete, resplices the steel. Then you know how much concrete you need to repair, how much steel you need to repair for that particular wall. But in a building like here, and particularly this building, it's a very complex building. It's a concrete building, it's a steel building with all kinds of dampers you will ever see in the wall. Okay? So then you have many, many items in the building. Okay? So in that situation, it's still not difficult for engineers to quantify every one of those components. What's the damage day for that? What's the damage day for this wall? What's the damage day for this ceiling? What's the damage day for every one of those items? At the end of it, you know the damage day for every one of those items. You can add it up. For this building, I know where the damage are. I know how much repair I need to do for the steel project, for the steel construction, for the concrete construction. And with that, you can go to a contractor and say, how much money does it take for you to repair 20 tons of concrete project for this job? And if you talk to one contractor, they give you a price, and maybe you have good relationship, you get a cheap price. And you have another contractor, they're going to give you something different. So there were variation in the construction cost as well. So in that situation, we don't want to just say with this must be the repair cost. So we look into two things. We were saying that we expected if you have to do a lot of repair, the unit cost, the cost per ton, cost per square meter may reduce. And we also accounted for uncertainties. If you're calling contractor A, contractor B, contractor C, there will be different price per unit. Once you know the unit price per unit, you know the total price, total quantity you need to repair, then you multiply that together, you get the repair cost. Okay? If you have contractor overhead, you add it up, so then you can get one repair cost. So in a building like this, I put in computer model, I run a ground motion, and I do a simulation of damage day for each one of those components, and I do the repair for this building. At the end of it, I get one repair cost. But your building owner didn't ask you how much money I'm expected to pay if this earthquake hits me. Okay? Chances are the earthquake will not repeat again. If you have another magnitude 7 earthquake hits me, is the price the same or different? Okay? You can rest assured it's going to be different, right? So if you try another earthquake, you will get another repair cost. If you try it again for another earthquake, you get another repair cost. If you do a simulation or all different kind of earthquake were likely to happen for that particular building you are assessing the condition for, you get a repair cost curve like this. The vertical axis representing money, how much money I expected to pay. The horizontal axis here representing how much money. So in this situation, if somebody asks me, how much money am I expected to pay if a magnitude 7 earthquake hits this building? Okay? The answer is that it could be as low as $500,000. It could be as high as $5 million. Wow, that's crazy. Why is there such a big difference? Well, the question is how much money I expected to pay if magnitude 7 earthquake hits me. There are so many magnitude 7 earthquakes were likely to happen, okay? And there are so many ways I can repair for it, okay? And there are so many ways I can trigger different damage rate along the building. So insurance companies started looking at this and say, how do I insure this building, okay? One way of doing it is say, well, on average, there are so many scenarios were likely to happen. On average, 50% probability. If I go there and I count down, well, you can actually be very confident telling your owners some earthquake damage will be low, some earthquake will be high. On average, it's about 1.8 million US dollars if a magnitude 7 hits me, my building. Some building owner will be happy. Now I have a number, 1.8 million. Is it good or is it not good? Insurance companies are usually more conservative. They call that maximum probable loss. So in a magnitude 7 earthquake, they usually look into the 90th percentile, and from here it comes down. So in this situation, basically the insurance company will evaluate the study and say, well, we look for the 90% confidence where your repair cost will be 3.8 million or less. So we'll insure you up to that amount, and then you decide whether it's good enough for your premium, okay? Well, that's one thing. If your owner is asking you how much money I expected to pay if a magnitude 7 earthquake hits my building. Some owner doesn't ask that question. Some owner says, I'm owning this building for the next 50 years. How much money I need to set aside so I know all risks of earthquake could hit me, okay? So if you are in this building, and for the next 50 years, you have chances to be hit by frequent earthquake, comes every 50 years. You also have some chances you will be hit by an earthquake which comes every 1,000 years. So if you really want to account for the next 50 years of operation, you started looking into the probability of all those earthquakes happening during the period of the time of your interest. A lot of the time, magnitude earthquakes, we change it into return period. Some earthquake comes every 72 years, some earthquake comes every 500 years, some earthquake comes every 1,000 years. With that, you have each one of these curves. Each one of these curves is the financial loss given the earthquake has happened. If you multiply the probability of this earthquake happened during the period you're looking for, or during that year you're looking for, and you add it up by integrated, by summing them up, you get what we call the annualized loss curve. By integrating the product of probability and multiply the probability happening, you get the total value, and the y-axis here now representing annual probability. Okay, every year, what's my probability? Horizontal axis here representing money. So in this situation, if you look here, 1%, basically you have around 1% chances on average, the repair cost for this building is $1 million. Average, on average, every year. Is that good enough or not? Okay, some owner says that, well, 1% is good enough for me. Some person says, no, I'm not happy with 1%. I want the 0.5%. Well, 0.5%, no problem. So basically, this one tells you 0.5%. Then you know if you put about $1.4 million in the bank, chances are you will not exceed that part of probability. Another thing which is quite useful, what we call this annualized curve, is the area under this curve. The area under this curve is on average, okay, how much money you'll be paying related to earthquake-related damage. So if you integrated this area, now you can say, some year I'll pay more, some year I'll pay less, and on average, I'm paying about $31,300 US per year for earthquake-related damage. Is that good enough or not? That's a decision making by the owner. So now we started having a language where we can start talking to building owner where they can set objective where they want to achieve. Okay? If the building owner will ask me, how much is my expected, well, on 50-50 chances, if a magnitude 7 earthquake hits me, I can give the answer now. I can do detailed simulation of ground motion, detailed modeling of structural response, detailed simulation of probability of damage day in all those components. On average, the financial loss is $1.2 million. If the building owner is not happy about 50-50 chances, you can say, I have 90% confidence where I study all these scenarios, the repair cost shall be 3.8 million or less. Very good. And then you can have a ways of showing the average cost, and you know where the financial costs are. Now the repair costs are shown item by item. You can actually show which item or which one is the troublemaker. So if I want to retrofit for this building, I know it's the east wing, third floor, that particular column I need to strengthen instead of just randomly strengthen every one of those structural components. You can also use this methodology in comparing which kind of structural design will be better performance. You can do a traditional moment frame, you can do a buckling strength brace frame, and you can do a moment frame with viscous damper, and you can compare the performance. This is one of the applications we have done at UBC. So this is one of the building. Yeah, so this is one of the buildings that were integrated. This is the Earth and Ocean Science building on our campus. So in that buildings, we developed a framework for users like yourself. Now we fully integrated with Google Earth. So now you can use Google Earth capability to put in any address. We even try North Korea. Thing shows up. We don't know if it's real or not, but you can go anywhere, okay? And sometimes sensitive area, you see a lot of cloud, always there. I don't know why. But now you can actually build a model with Google Earth now. And if you already have some database BIM model where Japanese have a lot of those, even information underground, load it. Okay? So you can create these models on the Google Earth. And then you can copy it. Well, this is 8 times speed. I expect that you will operate at the same speed. So once you have the models, we integrate it with OpenSeas, which will train very well. And you can integrate with any of the OpenSeas models. And you started looking into the structural and non-structural component. So we actually create an iPad app. Nowadays, it's your phone. This was done maybe 8 years ago, where phone was not so easy. So we developed an iPad app. You go to a building, you start taking photos. Every photo you take, the iPad will check where you are, where the location are, automatically pinpoint to your model. That item is in this location. At that time, 8 years ago, we have to do a lot of manual input, well, the dimension, the cost roughly on that. Today, we no longer need to do that. AI, take a picture, I know how much it costs, where it's made, everything will automatically be included in your database. And then, we integrated all the ATC 58 research team. Thanks for all the effort from Professor Maley, Professor Whitaker, many people. Over 10,000 components, or all the fragilities we have fully integrated then. So now you can say this particular component, select that fragility curve, and your run analysis no different than clicking the run and any finite element software now. So the computer program will automatically quantify the structural damage, the EDP, and do all the financial losses for you. Very good. That means I have to shut now. Anyway, yeah, I'm going to very quickly. Yeah. So those are now, and the future are so quick now. I have 0 minutes to present it to you. With the advancement of AI technology, now we can start seeing cars are driving by itself, automatically knows this is a car, that's a person. We have fully integrated that technology to autonomously having AI quantifying the damage state of those components. So this component, the AI automatically says, no problem, partial collapse, totally collapse. And we can use it for steel structures, concrete structures, and we started making our own robots in our laboratories to start going around and start doing inspection on its own. We use UGV, we're also using UAV, so we start making our own circuit board and integrate with different sensors, and we can check damage of earthquake damage. Now we can do fire damage, small damage, so to replace human for inspection. We have successfully, the other things that we have developed is autonomousness. So you don't want human to integrate your drones. So now our drone is flying around by itself without maps. So you will find doors and start going there. As you start going there, you start mapping everything around you. So we have successfully implemented the technology for the drones to fly around, identify damage, and tell you what damage state they are. And then we started using it for steel structures, concrete structures. We can see bolt loosening. And very soon you will see drones start flying around, identify types of structure system, timber building, masonry buildings. And then it will do autonomous assessment. If it sees a damage, it will have a solution for you for both short-term and long-term retrofit scheme. With that, let me give you a very quick summary and conclusion. So PBE, performance-based earthquake engineering, has started from dream, but now we went through the theory and started implementing it. PBE allows researchers and engineers to make risk-informed decision, so you can actually make the design towards any performance objective of your choice. Advanced PBE tools, the robots are already been developed. The future is now, and I'm pretty sure together we can actually make a very good impact and making sure the future infrastructure are designed to be safer, more economical, and resilient. With that, I thank you for your attention. Yeah, thank you. Yeah.